Okay, welcome to Let's Get to the Marks. Going through a question on Kc. Going to focus on how you work out the units in this question. It's a quick one. Let's get into it. Let's go. Ethene reacts with steam in the presence of an acid catalyst to form ethanol. We've got an equation here where we've got an ethene molecule in a gaseous state plus water in a gaseous state, reversible symbol, and then we have ethanol. Don't forget, once I've read the question, pause the video, have a go on a scrap bit of paper, and then watch the walkthrough. 1.1, write an expression for the equilibrium constant Kc. For this equilibrium, deduce the units of Kc, and it's worth 2 marks. All right, I'm going to go through it now. So you're always going to do products over the reactants. So don't forget you need square brackets. So we're looking at CH3, CH2 for our product, OH. We're going to put square brackets. It's Kc, so we're always using square brackets with Kc. If it's Kp, you're going to use rounded brackets. And then this is going over the top of C2H2, made that ugly, and then H2O. And that is Kc. So Kc is equal to the product over the reactants. Notice there are no coefficients, so I don't need to put to the power of for any of these. The next step is calculating the units. And I want to go through this. This is important. So when you're calculating the units for Kc, you're going to write concentration is always in moles per decimeter to the -3. And I've got one lot on top, and I've got 2 lots at the bottom. So look, I'm writing it out twice. And I know it's long. Some people just do this off the top of their head. Now, we're going to cancel one from the top, one from the bottom, because that's what you do. And that just leaves me with one here. But here's the thing. If you've got a dividing line and you've got the units at the bottom, what you're going to do is you're going to reverse the signs of the units. So the units are actually going to be mole to the -1 instead of mole to the 1. It's mole to the -1. And instead of being dm to the -3, it's going to be dm to the 3. Cool. So if you end up with no units at the top above the dividing line and only units at the bottom, you add them together, however many units there are, and you reverse the signs, i.e. the moles becomes negative, the dm becomes positive. Thought I'll go through that. Now, let me just give you another example. Give an expression for Kc for this equilibrium and state its units. So we've got another one like that. So what we're going to do here, again, it's products over reactants, but I want you to focus on the units. So we're just going to write out the products. This time there are coefficients. So we're going to do the products at the top. So we've got CO. What's the coefficient? It's 2. So you're going to put a 2 here. And then we've got hydrogen. What's the coefficient? It's 4. So we're going to put 4 there. Then we're going to put the line underneath. Oh my days. And then we're going to put ethanol. And we're going to put water. Okay. Now we're going to just work on what are the units. Yes, you can do the calculation. I'm not interested in that at the moment. So we're just focused on the units. Now, look, I've got 2 lots of units there. So if I was to write all the units out, let's be really long and write the units out.
If you push the button.
Like me.
Would you like it?
Like.
Okay, guys, check this out. Right, what I'm trying to show you here is you see I've got 2 lots of carbon monoxide, 4 lots of hydrogen. So there's actually 6 lots of mole dm -3. 1, 2, 3, 4, 5, 6. Oh my days, it's a lot. 1, 2, 3, 4, 5, 6. And down below, as there's no coefficients for the reactants and they're underneath, I've just got ethanol to mole dm -3 and water mole dm -3. So I've got 2. So what I'm going to do now, same as before, we're going to cancel out. So 1 above, 1 below, cancel out, 1 above, 1 below. How many does that leave? Well, that leaves 1, 2, 3, 4 on top. What we're going to do, we're going to add them all together to make the units. So if you have 4 moles, you're going to get mole to the 4. And there are 4 dm -3s. So 4 times dm -3 is dm -12. So notice when the units are on top and there's nothing below, you do not reverse the sign. So there was no reversal of the sign. This stayed as negative. We just multiplied or added them all up. And whereas with these guys here, we just added them all up. We didn't reverse the sign. So mole became 4, dm became -12. So the only time you reverse the sign when you're doing the units is when you are left with some units at the bottom on their own with the dividing line above them. then you're going to reverse the sign. And that's how we do the units of Kc. Right, let's get back to the original question we were looking at. It says 1.2, an equilibrium mixture was found to contain 0.7 mole of ethene, 1.2 mole of steam, and 4.4 moles of ethanol at temperature T. The volume of the container was 2 decimeters. Calculate a value of Kc for this equilibrium at this temperature. Give your answer to the appropriate number of significant figures. So all we're doing here, guys, we're doing this one here. So we've just got ethanol over the top of these two bad boys. There's no coefficients. So literally, I want to set this out like this, ethanol over those two. So it says I've got 4.4 of ethanol. Now, we're supposed to be doing concentration because there's brackets, right? So I need to do 4.4 divided by 2. Okay, and I'm going to divide that by the reactants. What have I got? I've got 0.7 of ethene. Okay, we'll be good. We'll write it out like that, and that's over 2. And we're going to multiply that by 1.2 of steam, and that is divided by 2. And if you want, that's the Kc. If you want, you can simplify that. If you're into simplification, then we can do like, that's going to be what? 2.20 over, what are my days? Over 0.350. And we're going to times that by, what's that? 0.60. And if we smash that all in our calculator, we're going to get Kc. Kc comes up as 10.476. And all I need to do is put this to the appropriate number of SF. A-level peeps, when they say that, they're telling you 3 significant figures. Don't mess about. So if I want to put this to 3 significant figures, I've got to push this up because of the 7. And that's going to make that 10.5. And that's the Kc, right? And we already said what the units would be. Yeah, there we go. Lovely jubbly. Don't forget sharing's caring. Hit the like, punch up the bell, subscribe. Let's get to the marks.
You still here? It's over.
Okay, welcome to Let's Get to the Marks, going through a physical chemistry A-level question on enthalpy change. Let's do it. Alcohols such as methanol, ethanol, and propan-1-ol are good fuels. We've been given their structural formulas. A student carried out an experiment to determine the enthalpy of combustion of methanol. Methanol was placed in a spirit burner and the mass of the spirit burner measured. The student placed 100 grams of water in a copper calorimeter and clamped it above the spirit burner. The burner was lit, allowed to burn for a few minutes. The flame was extinguished and the new mass of the spirit burner found. The measured temperature rise was 38 degrees. Specific heat capacity of water is 4.18. Figure 1, a diagram of the apparatus is shown alongside table 1, which shows the measurements the students recorded. Let's get a little bit more of this into the picture. So what is the question here, folks? Use the student's data to calculate an experimental value for the enthalpy of combustion of methanol in kilojoules per mole to the -1, 4 marks. We've been given the mass of the spirit burner containing methanol before the experiment, 214.02 grams, and the mass of the burner containing methanol after the experiment, 212.37 grams. And we've been given the apparatus setup. We've got a copper calorimeter, we've got water, we've got a clamp, we've got a thermometer, spirit burner, and some methanol in there with a wick. Okay, right. First thing I would do is grab a scrap bit of paper, grab a pen, grab a calculator, pause the video, have a go at the question, unpause, watch the walkthrough. Okay, let's get into the answers. So first thing I do when I'm approaching a question like this is I'd highlight any key points. So I'll be zinging through here. I'll be like, oh, enthalpy of combustion of methanol. We know that's kilojoule per mole down there. That's always in kJ mole -1. Methanol was placed in the spirit burner. Mass of the spirit burner measured. The student placed 100 grams of water. So what is 100 grams of water? It's the mass. So I've got M. Copper calorie, clamped it down. Bada bada bing, bada bada bong. Burn for a few minutes. We've been given temperature rise. Hopefully, you know by now the symbol for that is delta T. So we've got the temperature rise, delta T. And we've been given C, which is the specific heat capacity. And this should ring bells in your head. We are doing Q equals MC delta T. Now, Q is not actually our final answer, but it's going to get us at least 2 of the marks. So what we need to do is the mass times the specific heat capacity times the temperature change. And they've given all of those straight off the bat right here. Look, 100 grams of water. It's actually the mass of water is what the M stands for. So we want to do 100 times C, that's a really baby C there, times specific heat capacity of 4.18. So we're going to go 100 times 4.18, and then we're going to times it by the temperature change. Sometimes they give you the initial and the final temperature, or sometimes you've got to work out the initial or final temperature. But here they're giving us the actual change for us, so simplified things. So we just want to do 100 times 4.18 times 38, and that is going to give us 15,884 joules. Okay, now look at our answer. They want it, and it's always good to go down to the question and find the units they want. They want it in kilojoule per mole. So what's the first thing we need to do? We're going to change this into kilojoules. How do you change 15,884 into kilojoules? You know the coup. You divide by 1,000. And now we are going to get 15.884 joules. So next steps. This says mole to the minus 1. So I want to turn it into divided by moles. Mole to the minus 1 is in old money. Mole to the minus 1 over here is just kilojoule back in your GCSE days per mole. So when they write mole to the minus 1, that's what that means. So I need to divide that by moles. And how am I going to work out moles? Well, I'm going to come over here where I've got a bit of space, and I'm going to do mass over mR times moles. Now, you might get a little confused here and think you've got to use the mass of the water. No, that's what you're heating up. It's the mass of the fuel used. So I need to work out the mass of the fuel used, divide it by the mR, times it by the moles. I can work out the mass of the fuel used by the mass of our container here. And then afterwards, when we've finished, that's the amount that has burnt off, hopefully. Of course, there are reasons why some of the other mass may have escaped, but we'll get into that later. So I want to do that minus that. So let's smash that in the old calc. So 214.02. God, that don't look good in pink. 212.37. So if I do 214.02 minus 212.37, I'm going to get my mass of fuel, and that's 1.65 grams. That's how much methanol we used. So I want to divide that by the MR of methanol. Methanol is CH3OH. So C's 12, O is 16, and H is 1. So I've got what? 4 H's plus 16 is 20, plus 12. Is that 42? Is it more than that? I don't think I can add up. I think I've lost the plot. 16. Oh my gosh, I've lost the plot. 17, 18, 19, 20. Oh my good gosh, it's 32. Jeez, that took me a serious amount of time to add up. Right, well, that is times 4. So that should have been pretty easy, right? 4 times 1 plus 16 plus 12, 32. Let's smash that in the old calculator. And if we do 1.65 divided by 32, we are going to get 0.05156. So 0.05152625. That's the amount of moles. That's N. And all I need to do now is divide that by N, which is that. So I'm going to do 15.884 divided by my moles. So 15.884 divided by answer. Bing! I get 308.05. Now, yeah, that is kJ per mole to the minus 1. Now, whether you want to round that down, 3 significant figures, so we could do that to 310, or I'll just leave it as 308.05. Sounds good to me. 2 decimal places might be a bit nicer for that, so we could do it as that, or we could round it to 310. We'll see what the mark scheme says about that and then let you know. All right, and that's how you get your 4 marks. Right, let's move on to the next part of the question. So zinging down suggests one reason other than incomplete combustion of heat transfer to the atmosphere. So we're losing heat to the atmosphere all the time. You can't prevent that. You can minimize it with heat shields, with polystyrene, with lids, with all of that stuff. Why the student's value for the enthalpy of combustion of methanol is different from the data book. So we've got a couple of reasons why. And it's maybe we didn't do complete combustion. Oh, it says other than incomplete combustion or heat transfer. So need to identify those. So definitely highlight those. So you've generally got 4 reasons why you got 4 reasons in this experiment why we're not getting the same data book answer. And it's normally heat transfer. So I'm going to go up and show you guys. So it's normally heat transfer. Let's zing up. But this one says, like, don't write heat transfer. So essentially, instead of all of the heat from the methanol going into the thermometer and causing our 38-degree temperature rise, we're going to get an underestimation because our temperature rise is actually going to be smaller. So our Q that we calculated at the start is going to be a lot smaller. It's because heat is escaping into the atmosphere. Look, it's coming out of here. There's a flame here, but the heat is coming out of here. And so it's escaping out into the atmosphere. So it's not all going into that thermometer. We're not all going into the water, not causing that temperature to rise as much as it should. Another reason, which they said we're not allowed to use, is incomplete combustion. Incomplete combustion is when you make carbon monoxide or carbon particles. You'll know you'll get small black soot particles around the edges at the bottom of the beaker or the calorimeter. So incomplete combustion does not release as much heat. It's not as exothermic as complete combustion. So that's another reason why we wouldn't get such a big temperature rise, and why our answer doesn't match. But they've said we can't have that. So there are 2 things we can have. Methanol's an alcohol, and they are volatile organic solvents. They're going to evaporate. Even at room temperature, you'll get considerable evaporation. So we may have lost some mass through evaporation of the fuel. That's one of the reasons. And the other reason is here, what is this thing made of? It's made of copper, and copper's a conductor. So rather than putting it in insulating this is obviously you're trying to conduct the heat quickly into the water, but some of the heat goes into the copper to heating the copper. And here we go. So 2 possible answers. Some of the heat transferred into the copper metal or the copper calorimeter instead of the water. And then the other one is we had evaporation of the fuel. So there are our answers here. Normally, you can also say incomplete combustion, or you can say heat transfer to the surroundings or the atmosphere. So evaporation of the fuel, as it's a volatile solvent or volatile organic compound, evaporation of fuel, and heat transferred to copper calorimeter, whatever. Oh, yeah, it's hot today. 2.3, the uncertainty of each of the temperature readings from the thermometer in this experiment is plus or minus 0.25. This gave an overall uncertainty in the temperature of plus 0.5. Sometimes they'll get you to work that out yourself. So because we took 2 readings to get a change in temperature, so we must have had an initial temperature and a final temperature, we have double the error because you get 0.25 when you read the initial temperature, 0.25 when you read the final temperature. So our change in temperature has a total error or uncertainty of 0.5. Calculate percentage uncertainty for this thermometer in this experiment. So we want to do total error, which is 0.5 over 38, and we're going to times 100. And that is going to give us our answer, which is 1.316%. It's actually 315 something, but you're going to round that to 316. Coolio. Right, 2.4. The student said correctly that using a thermometer with an overall uncertainty for the rise in temperature and plus 0.5 was adequate for this experiment. Explain why a thermometer was adequate for this experiment. Well, the reason is we got a large temperature rise. So the temperature rise was quite big. Woo. The temperature rise was quite large. So you had a 38-degree temperature rise. It's not going to look so great if it's a smaller temperature rise, but the bigger the temperature rise, yeah, then that means that level of uncertainty plus or minus 0.5 degree. Hey, if you're having a 38-degree temperature rise, plus or minus 0.5 degrees, not too bad. If you've got a 2-degree temperature rise, then your level of uncertainty is going to be a lot more. Look, imagine we had a 2-degree temperature rise. We'd be doing 0.5 over 2 times 100, right? We'd have a 25% error. So that would be pants. The fact that we had a 38 degree temperature rise means our percentage uncertainty is quite low. So the overall uncertainty of 0.5 is acceptable for that large temperature rise. Coolio. 2.5. The enthalpy of combustion of ethanol is minus 1371 kJ per mole to the minus 1. The density of ethanol is 0.789 grams per centimeter cube. Calculate the heat energy released in kilojoules when 0.5 decimeters of ethanol is burned. Give your answer in the appropriate number of significant figures. So once again, what I do here, I just highlight some stuff. Okay, so that is my delta H, that's my enthalpy change, enthalpy of combustion, whatever, put a little C there. I've got density here. I'll be given volume. So straight away, we can do density times volume gives me the mass. And why is that? Because density equals mass over volume. So I can do D times V and give me mass. Then we can convert this. We want to convert this back to just kilojoules. Okay. So let me explain. Right. We've got a total of 500 grams. No, we haven't got 500 grams. Let's work out exactly what our mass is. If it was 1 gram per centimeter cube, we'd have 500. Right. My density, I need to align my units. So I've got 0.789 gram centimeter cubed. Now, I'm going to multiply that. That's my D. I'm going to multiply that by my V, which is 0.5, but the units don't align. Look, my volume units do not align. So I need to times that by 1,000 and turn that into grams. Sorry, off my rocker. Turn that into centimeter cubed. Now the units align. This is divided by centimeter cubed, and that is centimeter cubed. So we're just going to be left with our mass. And our mass here, which should get us the first out of 3 marks here for calculating the mass, 0.789 times 500. That is going to give me 394.5 grams. So I have 394.5 grams of ethanol has been combusted and released that. They now want me to work out how many kilojoules that was in that volume of ethanol. So this is the mass that released that. So I need to find out, I need to get rid of this mole to the minus 1. And what I'm going to do there is, I'm going to do, I need to find out the moles, don't I? Yeah, so let's find out the moles. So we're going to divide this by moles because mass over MR times moles. And we're dealing with ethanol this time. So I'm looking at C. Did they say ethanol? They said ethanol. C2H. Oh, yeah, there we go. So I've got 24 plus 5 is 29 for the 5 H's, and then plus 17. Oh, my days. Don't ask me to do maths. 34, 43, 48, right? Is that 48 or is that 46? That's 46, right? 17 plus 5 is 22 plus 24. Oh, my gosh, 46. Nearly screwed that up. Right. So why am I dividing it? I'm trying to find the moles, you Wally. So I'm dividing it by the MR of 46. So essentially, I want to find moles. And you might say, why do I want to find moles? Notice this is kilojoules to the mole minus 1. The unit they want our answer in kilojoules, right? They want our answer in kilojoules. We need to get rid of mole to the minus 1. So I need to times by mole. If you times mole to the minus 1 by mole, you get rid of the mole to the minus 1. And that's what we need to do. So we're going to go 394.5 grams of mass. We work that out by density times volume, divided by the MR of ethanol, which is 46. That is going to give me 8.576. And that's my amount of moles. So what I'm going to do is multiply those moles by minus 1371 kJ to the mole minus 1. And by doing the times in the moles, and that's dividing the moles, you're cancelling the moles out. And we're going to be just left with the kilojoules. So let's do that. What have we got? 8.5, my days, 76 times minus 1371. And that equals, I'm getting my reading is minus 11,757 kilojoules. Now it says appropriate number of significant figures. At A level, they love you to do 3 significant figures, people. So I want to round this to 3 significant figures. That 5 is going to push this up to 8. So it's going to be minus 11800. We only want The first three numbers that are important, they're the three significant figures. So it's 11,800 instead of 11,500 and 11,757. Jeez, I longed that out, peoples. There we go. 3 marks.
If you push the button,
Would you like it?
Like. Like.
You're still here? It's over.
Okay, welcome to Let's Get to the Marks, going through some organic chemistry for AS chemistry or year 12 chemistry, still relevant if you're doing year 13 chemistry. And we're going through some stuff on alkanes. So we have octane and isooctane are structural isomers with the molecular formula CH18. I don't know what I said there, that's structure moral. What the? Anywho. Octane and isooctane are structural isomers with the molecular formula CH18. The displayed formulas and boiling points of octane and isooctane are shown in figure 2. So we've got octane here. See there's 8 carbons. Then we've got isooctane, also 8 carbons, but we've got some branching. Boiling point's 99. Boiling point's 125. Try to be thinking in your head right now if they've both got the same MR and type of atoms and elements, same elements. Why has this one got a higher boiling point than that one? What must be the only reason? And we're starting off with give the IUPAC name for isooctane. So what you want to do is, first of all, you want to count how many carbons are in the main chain. By the way, you might want to grab a pen, pencil, have a go on a scrap bit of paper, and then unpause with each step of the video. Pause it, unpause, check your answer. All right, let's go. So we've got 5 carbons in the chain. So what are we saying, folks? That's got to be pentane, right? So we've got 5 carbons in the main chain, pentane. And now, if we exclude the main chain, we have a side chain here and a side chain here, and we have a side chain here. So how are we going to number this? Well, we want to give it the lowest numbering system possible. So probably 2, 2, dimethyl. Oh no, 2, 2, and we've got a methyl group on there as well. So we can't say 2, 2 dimethyl 4 methyl. We say 2, 2, 4 trimethyl pentane. That sounds good. Okay. So I reckon, folks, if I can get myself together. So when you're doing the numbers, put a comma in between each number. So it's 224, and then unless you're putting a comma between numbers, you're just using the hyphen or the dash, whatever that is. So 224, we want trimethyl pentane. Not pentane, pentane, don't know what happened there. Right, yeah, 224 trimethylpentane. There we go. You might say to yourself, why isn't it 244 trimethylpentane? Because 244 would create 2 4s, so that wouldn't be the lowest possible numbering system. The lowest possible number combination is 224. 442, if we went this way and called these 4s and that 2, wouldn't work. So it's 224 trimethylpentane. Anywho, enough of my whiffle waffle. Let's move on. So we have here octane and isooctane can be separated in the laboratory. Name a laboratory technique that could be used to separate isooctane from a mixture of octane and isooctane. Outline how this technique separates isooctane from octane. So you guys, oh, 3 marks, lovely. Right, so when you have more than one liquid, and we've been shown in the diagram that there were different boiling points, right? One was 125, one was like 99. Let's just check that again. So you were given that clue there, 99 degrees, 125. They're mixed together as colorless liquids. Well, we can separate them, of course, by fractional distillation. So we want to do fractional distillation. And it says outline how this technique works. So we want to say, basically, octane has a lower boiling point than octane. So we heat until at or just below 99 degrees, right, which is the boiling point of isooctane, the BPT of isooctane. I think I'm adding an extra O there. Am I adding an extra O? Was that spelt with one O or two O's? Isooctane. It's one. Oh no, it's two O's. Yeah, there we go. I need an extra O in there. That got a bit confusing there for a second. So it's isooctane. Basically, what does that stand for? Isooctane, it's an isomer of octane. So we heat it at 99 degrees, which is the boiling point of isooctane, or just below 99 degrees. And what this means is that only hopefully the majority of evaporation will be from the isooctane, and as it moves up through the beads or the fractionating column, it's the isooctane will move further and faster and evaporate first and condense first, and that's what will create the separation. So isooctane, oh my days, having a struggle here, will evaporate first and separate out in the column, or separate in the column. Yeah, and be condensed off first. So you're going to condense off the one with the lower boiling point first. Once that's done, you can boil the other one to your heart's content and get rid of the other one as well. So fractional distillation, we want to point out that we're using their boiling points, and the lower boiling point one is condensed off first or separates first in the column. I don't think I worded that too well, but there we go. Right, let's check out 3.3. Isooctane is added to petrol to increase its octane rating. Some high-performance engines require fuel with a higher octane rating. Write an equation for the complete combustion of isooctane. Use the molecular formula C8H18. So this is bang easy, right? These are the easiest balancing equations you can get. Yeah, they still come up in A level, in A2 as well, come up in the multiple choice questions, and sometimes within the STEM, within a single part of an overall big question. So with combustion reactions, and it's complete combustion. So this is where we got to highlight. It means that all of the carbon and hydrogen has reacted to form carbon dioxide and water. And all we have to do here, the reason why these are the most favorite balancing equations is because you just go C8, right, a bash an 8 in front of carbon dioxide, and you go H18. Well, in order to make 18 H's here, as I've got H2, you always just put half whatever the hydrogens are there. So we're going to put 9 there. Now that means we've got 8 carbon dioxides and 9 waters. And if we add up all the oxygens there, that's 8 times 2 is 16. 9 oxygens added to 16. We've got 25 oxygens, right? Now, you come back over here and you always do the oxygen last, because the oxygen will always depend on how many carbon dioxides or waters you're making. So I've given myself a little space there, and I'm going to put 12.5. Obviously, you need to write a little bit neater than that, but that's 12 and a half oxygens. Now, some people, for some crazy reason, don't like to deal in like decimals, but you're allowed in these combustion reactions too. But if you have to do a multiple of it, just times everything now by 2. So you'd have 2 of that, 25, 16, and 18. But let's be honest, in A level, you can use decimals when you're doing, you can use halves when you're doing combustion equations. Explain in general terms how a catalyst works. Now you might say, why is it saying in general terms? What does that mean? It's what's your A level? What are the 2 things a catalyst does at A level? They're not wanting you to get into homogeneous, heterogeneous catalyst adsorption to the surface. This is just basic stuff of how a catalyst works. So you all know it lowers activation energy. And then we can say by providing an alternative route. So it lowers the activation energy by providing an alternative route, by providing a surface for the reactants to react on that has a lower activation energy. There's like different ways that you could write that, or you could just say alternative route. Okay, let's zing. Okay, going the wrong way. Not for the first time. 3.5. Carbon monoxide is produced when incomplete combustion takes place in engines. Nitrogen monoxide is another pollutant produced in car engines. Write an equation to show how these pollutants react together in a catalytic converter. So this one's got, there's a misconception we're going to come across here. So we've got carbon monoxide is made when incomplete combustion takes place. Nitrogen monoxide is also made when combustion takes place. These are both pollutants, right? They're harmful to living organisms. Write an equation to show how these pollutants react together. So we're going to react them together in a catalytic converter. For those of you who want to know, catalytic converter is, well, yeah, what happens. Okay, catalytic converter is like this thing on the bottom of your car. It's probably worth a couple of £1,000, can be, or £700-800, depending on what car you've got. It has precious metal in there. And what happens is the nitrogen monoxide here, they've given us, it could be trioxide, dioxide, it's all sorts of ones, and carbon monoxide go in here together on their way out. So they don't make it to the atmosphere. They're coming from the engine, running down a pipe underneath the car, and then they're going to come out the back of the car where you see all that gas coming out of the back of cars, the exhaust. But before it can come out the back, it has to run over this catalytic converter, and this is going to convert them into slightly, well, not pollutants. And this is what people are going to make a mistake on. It converts it into carbon monoxide and nitrogen back in the air. They're going to say to themselves, but isn't carbon monoxide, isn't carbon dioxide a pollutant? No, it's a greenhouse gas. It's actually not harmful to living things. If we didn't have carbon dioxide, we'd all be dead because there'd be no photosynthesis and no plants could grow. So carbon dioxide is not a pollutant. Anywho, enough of my whiffle waffle. Let's do NO plus CO, and we want to make this into CO2, and we want to make that into N2. Now, because I've got two nitrogens, because it's a diatomic molecule, I need to put a big fat 2 there. So I've got 2NO. What else does that mean? I've got 2 there. I've got 1 there. Got 2 there. I'm going to need to bash this up to 4 because that makes 4 oxygens, and then come back over here and put a 2 in front of the carbon monoxide, and then that means altogether I've got 2 times O, 2 times O, 4 oxygens, 2 times O2, 4 oxygens, got 2 times C, 2 times C, and I've got 2 N's, and we've got N2 there. Yeah, we're coolio. We're coolio. Right. 3.6, platinum, palladium, and rhodium are metals used inside catalytic converters. A very thin layer of metals is used on a honeycomb ceramic support. That was my attempt at like a kind of lattice, or, you know, like honeycomb. It's a bit 3-dimensional. That looks 2D. Explain why a thin layer is used in this way. So we can get a large surface area. We can make a large surface area for the reactants to collide upon or react upon. Essentially, you've got something called adsorption, and the gases can adsorb to the surface. The larger the surface area, the more space there is for them to absorb, for the nitrogen monoxide and carbon monoxide naturally come into contact and react and become nitrogen and carbon dioxide. And once they react, they desorb from the surface. Now, why do they use a thin layer? Well, these are precious metals. They're very expensive. So a thin layer means we only need a small mass or small amount of atoms of the precious, uber expensive metal. So obviously doesn't need to be, it only needs a thin amount of metal for them to react on. Okay, we don't need to spend millions of pounds on our catalytic converter. They're expensive enough with just a thin layer. Okay, well, I would be okay if I didn't keep ticking the wrong thing. Right, oleic acid C18H34O2 is a straight chain fatty acid obtained from plant oils. Isooctane can be made from oleic acid. The skeletal formula of oleic acid is shown here. So this is oleic acid. Okay, straight chain, i.e., what does that mean? There's no branches coming off the sides. Identify a reagent that could be used in a chemical test to show that oleic acid is unsaturated. Well, you can pause the video, have a go at this. Okay, what you should identify straight away is we got the double bond. So we got the old carbon-carbon double bond. And you learned this in GCSE. What identifies alkenes or unsaturated carbon-carbon double bonds? We want to use bromine water. And the observation will go from, oopsie, from orange to colorless. Okay, let's move on. Okay, welcome to Let's Get to the Marks. Going through another organic A-level chemistry question. This one's about mass spectrometry and intermolecular forces. Let's get into it.
Chemistry.
Yeah, baby.
The compounds in Table 2 all have a relative molecular mass of 58. Table 2 shows these compounds. We've got propanol. No, we've got propanal. We've got prop 2N1-ol. So the N stands for the double bond, the ol for the alcohol group. And we've got butane, 4 carbons. 4.1, explain why determining the precise relative molecular mass of propanal here and prop 2N1-ol here by mass spectrometry could not be used to distinguish between the samples of these two compounds. And the reason being they have the exact same number of atoms of each element. So they have the exact same molecular formula. They have the exact same number of atoms of each element. And guess what? They also have the same MR. So these are the two reasons why mass spectrometry is not going to work Problem is with using mass spectrometry to try and distinguish between them, the M plus peak, remember that peak right near the end, the M plus peak that gives you the MR of the M plus fragment ion, it's going to be identical for both of them. It's going to be in the exact same place. Now, the question isn't saying how do you identify between them and can you use mass spec to distinguish between them? You could distinguish between these two compounds due to fragmentation patterns, but you couldn't distinguish between these compounds using the precise relative molecular mass because they both have the same molecular mass, they both have the same atoms and the same number of each element, basically C3H6O. So yeah, there we go. You're not going to be able to distinguish between them based on the mass spec alone by determining the precise relative molecular mass. Is not going to help you. You're going to need to use a fragmentation pattern. 4.2, the infrared spectrum of one of these compounds is shown in figure 4. Transmittance, we got the wave number. Use the spectrum to identify the compound. State the bond that you used to identify the compound and give its wave number range. You should only consider absorptions with wave numbers greater than 1,500. They don't want us looking at any of these parts here. So what we're going to do, we're going to need to find a little data book, which is over here. Look what we find. 3,300 is going to be not that. Where is it? There, looks like that, an alcohol. Yeah, 3,300 is bang smack roughly in between 3,230, 3,550. So that is going to be a bond representing the alcohol. Now, we only find that bonds in prop 2N1-ol. Look, it's the only one with the OH group, so it's the only one of those isomers that could have made that pattern there because it has a peak at 3,300, which is the OH bond. So what I want to say is this is, oh gosh, prop. So we're looking at prop 2N1-ol. It's always long doing organics and putting all these hyphens in. Bond used to identify. So I looked at the OH bond. We could have looked at the double bond as it's the only one with a carbon-carbon double bond, the alkene bond. Wave number range of the bond, right? What was it? 3,230 to something like 3,230 to 3,550. I've got a brain like a sieve. It's like a listen. It's like a rice sieve. I can't even I've already forgotten what this was. I'm going to go 550. And if I've lost the mark, I've lost the mark because I've already forgotten what the range was. I think I might have to get my head checked. Okay. To get this, you probably need two of these will get you 1 mark, and all three will get you all 2 marks. Yeah. Okay. Zinging, zinging, zinging. 4.3. Predict the relative boiling points of these three compounds from the highest to the lowest boiling points. Justify this in terms of intermolecular forces. So let's just go in order, peeps. Which one has got the lowest boiling point? Well, the one with the lowest boiling point is going to be butane. And if you check this molecule, the only thing that you have between two butane molecules is weak van der Waals forces. Okay. Temporary dipole-dipole forces formed by random movements of electrons. Covered that in other videos. Random movements of electrons create temporary dipoles, which are induced into the neighboring butane molecule, and then you get a weak force between the delta negative and delta positive. And so that is going to have the lowest boiling point. The second lowest boiling point is going to be propan al, which will be higher because propanal has this here. Have a look, see. Propanal has a polar bond. It can't do hydrogen bonding because you need oxygen with nitrogen, fluorine, or hydrogen, and it's not bonded. It's bonded to carbon. But that is definitely more electronegative than the carbon and withdraws electrons, making that delta negative, delta positive. And we actually have a permanent dipole going on here, or dipole-dipole bonding. So that is going to have a higher boiling point because those are stronger than the weak intermolecular forces between butane molecules. And then lastly, but not least, in fact, the one with the highest boiling point is going to be prop2n1ol. Why? Because it has an oxygen attached to a hydrogen. Now, if you have oxygen attached directly to a hydrogen, a fluorine. So if you have a hydrogen atom directly attached to an oxygen, a fluorine, or a nitrogen, you will engage with hydrogen bonding between adjacent molecules, and this will give you higher boiling points as it's the strongest intermolecular force. What we need to do is put that all down as an answer and smash out the 6 marks. Let's go. Okay, justify this. So we want to say butane has VDWS, van der Waals forces only. These are the weakest intermolecular force. Now, it doesn't ask me to explain it, and I won't get any marks for explaining it. So why am I going to do it? Well, it's for your benefit, really. So I'm just going to go through and explain how these weak temporary dipole-dipole forces actually appear. So these forces arrive due to three things. If it was a separate explanation for how do you get temporary dipole-dipole forces or van der Waals forces, you'd say random movement of electrons create a temporary dipole. Well, delta negative, delta positive on part of the molecule, which then induces a temporary dipole in a neighboring molecule. The key word there is to induce in the neighboring molecules because electrons repel other electrons. And this means we get weak intermolecular forces between delta negative and delta positive. So here's two butanes. One end becomes negative, the other positive, forcing the opposite end to go positive, that end negative due to repulsion of electrons. And then the third mark, we get a force between. But you don't get anything for that. So I'm just going to highlight what you would get the marks for, which is what I'm supposed to be doing in the mark scheme, right? So these forces are easy to break, easy to overcome because van der Waals forces are weak. So this is why it has the lowest boiling point. So technically, we just needed to say butane has only got van der Waals forces, which are the weakest intermolecular force. Therefore, not a lot of energy needed to break the forces, easy to overcome. Lowest boiling point. You need to say that it's the lowest. And then the second lowest boiling point, or the medium middle boiling point out of the three, is propanal. And why? Because propanal has a polar bond, which means it has permanent dipole-dipole forces. It doesn't have the temporary ones. The van der Waals force has got permanent ones. There's a permanent dipole there, not due to the random movement of electrons, but due to the difference in electronegativity between the oxygen and the carbon, the polar bond on, And then that has slightly stronger forces between the molecules, more energy to break, so it has a higher boiling point than butane. And then lastly, the prop2n1ol, if I've got that right, is an alcohol. And alcohols contain the hydroxide bond, which is an OH bond. And if you have a hydrogen atom connected to either oxygen, nitrogen, or fluorine, the three most electronegative elements in the periodic table, you'll be able to do hydrogen bonding, which is the strongest of the intermolecular forces. Therefore, more energy needed to break. It has the highest boiling point. Whew. Sharing's caring. Hit the like, punch up the bell, subscribe. Let's get to the marks. Okay, welcome to Let's Get to the Marks. Going through a question on free radical substitution. So let's get into it. Okay, refrigerants are substances used to cool refrigerators and freezers. Until recently, many of the compounds used as refrigerants were chlorofluorocarbons, known as CFCs. But these are now known to form chlorine-free radicals. CFCs have been phased out in many countries by international agreement. 5.1, write two equations to show how chlorine-free radicals react with ozone molecules in the upper atmosphere, and this one's worth 2 marks. Okay, let's get into this one. Don't forget, you should grab some paper, a pen, pause the video, have a go, then unpause, check out the answer. All right, let's go. So first of all, we're told here how chlorine radicals react with ozone molecules in the upper atmosphere. So we want to start from the point where we have chlorine radicals. How do we get chlorine radicals? This is not your answer, but chlorine radicals are formed when ultraviolet light breaks that chlorine bond in a diatomic chlorine molecule, and you end up with two of these bad boys. You end up with two chlorine-free radicals. So we're being told, how does chlorine-free radical react with ozone? So we want to go chlorine-free radical plus ozone. And the problem with these chlorine-free radicals is they undergo a propagation reaction, right? So whatever we do as our outcome here, we need to make sure that we also have another radical formed. And here it is. We have a ClO chlorate kind of radical, and we have O2. So the ozone, which protects our atmosphere from harmful ultraviolet rays, which they absorb, has now been broken down into oxygen, damaging the ozone layer and forming another radical. Now, for the second reaction, we want to show this radical going back, because this is a propagation reaction up here. We want to show this radical going back and reacting with another ozone molecule and showing another propagation reaction. So this time we're going to get a chlorine-free radical formed. And again, that ozone is going to be broken down into oxygen. But now we've got 4 oxygen atoms. We're going to have 2 molecules of oxygen. So there we go. Propagation again. Lovely jubbly. And that's the harm of CFCs to the ozone layer. Right, let's move on. 5.2, chloropentafluoroethane is a CFC that has been used as a refrigerant. Draw its displayed formula. So that means they want us to show all the bonds. And it's all in the name, isn't it? It's pentafluoroethane. So we just start from the fact that it's ethane. So that's your starting point. You've got 2 carbons. And then it says pentafluora and 1 chlora. So we can stick the chlora on wherever we like. It doesn't matter. And then 5 fluorines. Easy as you like. And you just check that each carbon atom has 4 bonds. Remember, they have 4 valence electrons. So you can only form 4 bonds around a carbon atom. So 1, 2, 3, 4, 1, 2, 3, 4. We're all good. We've got 5 for the pentafluora and we got 1 for the chloro. Lovely. Let's move on. Don't forget to pause the video and have a go before each question. 5.3, 111 trifluoroethane, CF3CH3, is one of the molecules that's been used as a refrigerant in place of chlorofluorocarbons, CFCs. Explain why 111 trifluoroethane does not lead to depletion of the ozone in the upper atmosphere. And the reason is it doesn't contain, what doesn't it contain that a CFC? A CFC is a chlorofluorocarbon, and we've just drawn a chlorofluorocarbon, right? We just drew this. Look, it's got chlorine atom. But if we look at what they're telling us, 111 fluoroethane would look like this. Let's check it out, yeah? It's going to look just like this. They're not asking you to draw it, but it's all part of the old explanation, right? So we're drawing it out. Oh my days. That bond is coming out the bottom of the carbon atom. Don't know what's happened there. Look at that dodge. Right. So if we look at this, what's missing from it that was in our other molecule? Well, whoopsie. Yeah, it doesn't have the carbon chlorine bond. So that's one route to getting the answer, to say it does not contain CCl bond. So does not form Cl radicals. Like, it can't form chlorine radicals, can it? Chlorine free radicals, because it doesn't contain the CCl bond, so that can't happen there. And also, what do we know about the carbon fluorine bond? Now, you might think, and you'd be incorrect, but you might think that because this is so polar and it is a very polar bond, because fluorine's the most electronegative element, that's delta negative and that's delta positive, you might think that this means this is more likely to be attacked, but it actually comes down to the bond enthalpy and the carbon. So another way to answer this is the carbon fluorine bond is much stronger or has a higher mean bond enthalpy than the carbon chlorine bond. So is unlikely to break. So does not break in the upper atmosphere. Basically, the energy from the ultraviolet light, whatever, blah, 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 is not going to break that bond, the CF bond, whereas the Cl bond is much easier to break as it has a lower mean bond enthalpy. So we could go down the bond enthalpy route, or you could just say it doesn't contain carbon chlorine bond. There we go. Either one's good. Sorry, I've got this chest infection at the moment, so I'm breathing like a 90-year-old smoker. 5.4. One of the steps in the synthesis of 1,1,1-trifluoroethane CF3CH3 is the reaction of 1,1,1-difluoroethane with fluorine in a free radical substitution reaction. Write two equations to represent the propagation steps in the conversion of CHF2CH3 into CF3CH3. So we want, we want to do two equations to represent the propagation steps that convert this into this. So we're basically being told the first propagation step must contain this as a reactant. And in the second propagation step, we want this as the product. So I know that my propagation step starts here because it says write two equations that show the conversion of that to that. So I know that that must be the reactant in the first equation. And I know that in the second equation, I must be forming CF3CH3, right? Because it's saying that's going to get converted to that. So what can this react with? Well, it says one of the steps in the synthesis of 1,1,1-trifluoro is the reaction of 1,1-difluoroethane with fluorine in a free radical substitution. So they tell us it's free radical substitution. So guess what? We're going to have a fluorine free radical because they've told us it's fluorine, it's free radical substitution, it's propagation. All propagation steps start with a free radical. So when you see the word propagation, it starts with a free radical and create a free radical. So I need to create a free radical here. And so what we're going to do, we're going to join that F. It's going to steal this H here. So we're going to go C, F2, CH3, and we're going to have that as our new free radical because it now has an unpaired electron, and we have hydrogen fluoride. Now, why did I need to form this? Because I need to eventually get to that. And what's missing? What do I need to make that CF3, CH3? What do I need? I don't need another H. I need another F. I need another fluorine to make that CF3. So just compare those two there. So what I'm going to do is I'm going to start my second propagation step using the free radical made in the first propagation step. And I'm going to add a fluorine to it. The problem here actually is if I add a fluorine free radical, what's going to happen? I'm going to make that, and that is a termination step. So that could happen. This is a viable step, but this would be a termination step. Yet they've used the word propagation. So what this tells me, propagation tells me that it forms another free radical. So I have to have a rethink here, okay? It forms another free radical. So what I'm thinking is we go back to the board up here and we just have a fluorine molecule get attacked by that because we've got fluorine knocking about. So we have a fluorine molecule get attacked by that. That will, one of the Fs will go there and it will produce another fluorine free radical, which can go back to the start, attack another one of those. Yeah, there we go. Lovely. So just make sure you check out whether it's a termination or propagation. If it's propagation, you need one free radical on either side of the arrow. All right, let's move on. Okay, 5.5. A refrigerator contains 1.41 kilograms of 1,1,1-trifluoroethane. Calculate the number of molecules of 1,1,1-trifluoroethane in the refrigerator. Give your answer to an appropriate number of significant figures. They've given us L, which is Avogadro's constant, 6.022 times 10 to the 23 mole to the -1, and it's worth 2 marks. So I really want to work out, when you want to work out the number of molecules, you just want to do this. So number of particles equals Avogadro's constant, 6.022 times 10 to the 23, times moles, or times n if you like me and you like to use lowercase n. So the number of particles is L times n. So calculate the number of particles of that. Well, we've been given the mass, so I'm definitely going to need to do mass over mR to get moles, and then I can shove the moles up there, times it by L, and get the number of particles. So why don't you pause, have a go at that. All right. First of all, we need to convert the kilos here into grams. So 1,410 grams. We're going to divide that by the MR over here. So work out the MR. That's 12, 15 for the CH3. So CH3 is 15. 3 19s, what's that? 57 plus 12 is 69. So CF3 is 69. Oh my God, is that supposed to be equals 15? Yeah. So 15 and 69 is 7984. So bish a bosh. And if I do that, I'm going to get something along the lines of 16.7857 as my moles. That's N. Let's keep that all in the calculator. Now let's times that by Avogadro's constant, because we want to do N times L to get the number of particles. So times 6.022 times 10 to the 23. Smash that in the calculator. And we're going to get something along the lines of 1.0. Hold on. I just deleted my calculator. Working out 7857 times 6.022 times 10 to the 23 equals 1.01. I nearly thought that looked like a 6. 1.01. Oh, I don't know. I got 0.83 blah, 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 something times 10 to the 25. I can probably just round that to 1. What do we want to do? 0.1 times 10 to the 25. Let's move on. That would get you all the marks. (5.6) There are growing concerns about the use of 1,1,1-trifluoroethane as a refrigerant, as it is a greenhouse gas that absorbs some of the Earth's infrared radiation. Give one of the reasons why bonds in the molecule, such as carbon dioxide and 1,1,1-trifluoroethane, absorb infrared radiation. So once again, got to draw it all out for you peeps and just show you the types of bonds that are really good at absorbing infrared radiation. And you're looking at bonds that are polar. So what we're looking at here, guys, is we've got fluorine, which is seriously electronegative. And that means the carbon and the fluorine have difference in electronegativity. They make a polar bond. And we find that polar bonds vibrate, and this allows them to absorb infrared radiation. So we want to say CF bond is polar, it vibrates and absorbs IR, or infrared radiation. Infrared radiation. So if you have very polar bonds, they're very good at absorbing. Due to the vibration of polar bonds, they absorb infrared radiation. Bloody, 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 blah. Okay. That was just a quick little question on free radicals. So what can I say? Sharing's caring. Hit the like, punch up the bell, subscribe. Let's get to the marks. Don't forget, exams are coming. Do me a big favor. Hit the like.
Would you like it?
like, like.
Okay, welcome to Let's Get to the Marks. Going through a quick organic A-level chemistry question on reflux. Let's get into it. Let's smash those exams, guys. All right, question 6. Propane 1,2-diol has the structure CH2OH, CHOH, CH3, and that's the structural formula. It's used to make the polyesters and is one of the main substances in electronic cigarettes, e-cigarettes, so your vapes and stuff. A sample of propane 1,2-diol was refluxed with a large excess of potassium dichromate 6 and sulfuric acid. Draw the skeletal formula of propane 1,2-diol. This one's a nice easy one. So what I suggest, grab some paper, grab a pen, you know the coup, pause the video, scribble it out, unpause, check your answer. All right, let's go. Propane 1,2-diol. So propane means we have 3 carbons in the chain. 1,2-diol, I can put the OH group anywhere on the first or second carbon. It doesn't matter whether you start from the right or the left-hand side of the chain. The numbering always goes in the lowest possible way. So it doesn't really matter if my OHs are anywhere else. And there we go. Propane 1,2-diol. The 1,2 stands for the 2 carbons, diol for the 2 alcohol groups or hydroxide groups. Right, 6.2, write an equation for the oxidation. Write an equation for this oxidation reaction of propane 1,2-diol under reflux using O to represent the oxidizing agent. Show the display formula of the organic product, and it's 2 marks, right? So we don't need to write out potassium dichromate, which is our oxidizing agent. We just need to use an O for every oxygen we need. Now, our reactant is propane 1,2-diol, and there's a key here. So make sure you always circle and identify key things. Even in the most simple sentence, there might be something that helps you understand what to do. Okay, propane 1,2-diol. Look, they've given us we can just copy this here, right? So that's kind of groovy for us. So we got CH2, write an equation, all right, and then show the display formula of the organic product. Right, I'm not going to show the display formula of this, but I'll show the display formula of the organic product. Oh my days, this is the most awful, yeah, you know what I'm saying. I'm pretty poor at the old writing here. Okay, so there's our propane 1,2-diol. Okay, now they've said use the O as the oxidizing agent. So that is our potassium dichromate. Now, when you oxidize an alcohol, and we've got a primary alcohol here, look, this is a primary alcohol. And we've also, interestingly enough, got a secondary alcohol here because this only has 1 hydrogen attached to this carbon. So this is like a secondary alcohol, and this is a primary alcohol. I mean, it's probably easier to do it like that. That's a primary alcohol, and this is a secondary alcohol. Now, how should that affect us? Well, that affects the product that we're going to make, right? So let's zing the arrow. And this means I'm going to put the number and balance this oxygen after because I don't know how many oxygens I'm going to add yet. We're under reflux. What does that mean? That means the oxidation goes to its full maximum oxidation potential. So a primary alcohol, we can oxidize that to what? An aldehyde. And then we can oxidize that further to a carboxylic acid. So really over here, I want to change this to a carboxylic acid. Okay, so I'm going to keep my OH group or whatever, but I'm going to put a COO. So we've got carboxylic acid there. I'm sure I should have done the O up there and the OH down there. Maybe it looks a bit nicer. Yeah, whatever, it doesn't matter. Now over here, so there's my carboxylic acid. Remember, that's because this is a primary alcohol and we're refluxing it. So it's not just going to go to an aldehyde, it's going to go to a carboxylic acid. Now over here, I've got a secondary alcohol. This can only be oxidized to a ketone. It cannot make it to a carboxylic acid, and obviously it can't go to an aldehyde. It's not at the end of the chain, so it can't make it all the way to an so I just need to put an O there, and then all I need to do for the rest of this is, that's 4 bonds around there, is just Smash this all up. Now, here's the tricky bit, right? You're going to get a mark for that displayed formula for working out that. So well done to yourself. Well done to me. Woohoo. Here's the tricky bit. How many oxygens? And this takes a little bit of skill because if you look at this, first of all, you're like, right, there's two O's there. You've just added one O, Tom. It's cool. 1, 2, 3. You've added one O. But how many hydrogens are on here? 1, 2, 3, 4. How many hydrogens were over here? Check it out. 1, 2, 3, 4, 5, 6, 7, 8. So we've lost 4 hydrogens. What's happened to those 4 hydrogens, guys? What have they become? Hydrogen gas? They've become water. So there are 2 water molecules being given away. And that means we need another 2 oxygens for those water molecules. So not only do I need this extra oxygen here, but I need another 2 there. So I need a 3 in front of that. And that is going to get me the second mark. So just make sure when you're doing oxidation, that counts as losing hydrogen as well, because when you lose hydrogen, they go on to form water with the oxygen. So there we go. 2 marks. Lovely jubbly. Right, let's move on. Bum, bum, bum. Don't forget to hit the like, people. It helps out the channel massively. It helps me to help you get the tip-top grades. All right, 6.3. Draw a label diagram to show how you'd set up the apparatus for refluxing. Now, a lot of people don't know how to do this. Nice and easy. It's 2 marks. All we need is a pear-shaped flask. Do we have to do a pear-shaped flask? Yeah, you could do it. You could do a round bottom. I'm going to do a round bottom flask like that. But you could do a pear-shaped flask if you prefer pear-shape. So it's just like a heart or a shape of a pear like that if you want to do that flask. So you could do that one if you prefer. Okay, I'm going to go with the round bottom flask instead of the pear shape. So here's my round bottom flask. Up it comes here. Now what we need to do, we need to get our condenser and stick our condenser into it. So our condenser comes in like this. I need to make sure that bit's clamped tight. So you might want to stick a clamp on. That is some dodgy drawing of a clamp. There's my clamp. Oh my days, I should be typing. Now, with your condenser, you need, let's just draw that going all the way up. Okay, there's my condenser going all the way up. Right, this is the important bit. Show the walls are sealed like that. Okay, and they mustn't cross over here and they mustn't be open like that. They have to, you have to show they're completely sealed. And you want the water coming out of the top. And you want your cold water coming in at the bottom like that. Leave this top open because it relieves pressure. It allows vapors to escape and stops dangerous pressure buildup. This should be sealed tight here. There shouldn't really be a gap there, but it's my crusty drawing. So I've got my clamp. You don't need to label. It doesn't want, I don't think it wants, draw a label diagram. Oh, sorry, my mistake. Yeah. Round bottom flask. You can use a pear-shaped flask here as well. This over here is my condenser. This is a Liebig condenser. Liebig! Okay, there's my Liebig condenser. And then what we're going to do here, we want water in at the bottom. Now, you will lose a mark, maybe not in this particular diagram, but when you're discussing reflux, if you don't say that the water in is at the bottom and the water out is at the top. So water out coming out here. And there's a specific reason for this. Okay, so water in, what happens is the water is pushed up against gravity and it completely fills this. Okay, completely and utterly fills this, and you get the maximum heat exchange. As this is coming up, the water's at its coldest here, we're getting the greatest transfer of heat, and this is completely filled right to the top. If the water came in here and came down, this top bit would not really be filled. And so we'd actually get more stuff escaping and less transfer of heat. Anywho, that's my diagram for the Liebig condenser. And I believe they're going to give you the marks for the condenser drawn correctly like that, not crossing over from the tube, top unsealed, and a round bottom flask like that. You probably don't need the clamp. You might not even need the water in, water out in the correct way. Yeah. Anywho, let's move on. Okay, anti-bumping granules are placed in the flask when refluxing. Suggest why these granules prevent bumping. So, where are we? Oh my days. Look, check out my flask. Yay. So what do? We stick in some anti-bumping granules, and what they do is they break big bubbles like that into smaller bubbles. And why is that important? Well, it's important that you only get small bubbles in the flask because big bubbles obviously increase pressure buildup, but they also might spit some of your reactants up here into the condenser and even out here. So we don't really want big bubbles because they'll be spitting and bubbling, shaking the equipment, rattling and rolling. And so the anti-bumping granules break up big bubbles into smaller bubbles. Anywho, I longed that out, didn't I? All I need to do is say break up large, oh my days, large bubbles into smaller bubbles. That kind of easier just to say that. Okay. Draw the structure of a different organic product formed when the acidified potassium dichromate is not in excess. So if the acidified potassium, we don't have as much of the oxidizing agent, instead of getting the carboxylic acid, we're going to get the aldehyde. So I'm going to go for that version. I'm going to go for, look, I drew carboxylic acid from the alcohol, but instead I'm going to say, well, hey, the primary alcohol, I'm going to say this just goes to an aldehyde. So it goes like that. And instead of having an OH here, I'm just going to do an H there. What was it? Propanediol. So really anything that shows it hasn't oxidized to its full potential. So I could keep the OH there if I want and just show aldehyde. There's quite a few different ones, or I could show that that's gone to ketone. So this one could go to its ketone. That's the only oxidation it can do. Or you could keep that as an OH if you like, and just show that has been oxidized to an aldehyde. So we're just showing the oxidation hasn't gone as far because there's not enough oxidizing agent. Okay. I'm just going to do that and say, well, it hasn't managed. This hasn't managed to go to carboxylic acid. So if it went to full oxidation, you get a ketone form there on the secondary alcohol, and on the primary alcohol group, you would get a carboxylic acid. I'm saying it doesn't go that far, and that is my version to get the 1 mark. But there's several options in the mark scheme. I suppose we could keep that as an alcohol there. All right. Sharing's Kevin, hit the like, punch up the bell, subscribe. Let's get to the marks. Okay, welcome to Let's Get to the Marks. Going through electrophilic addition of alkenes, looking at the electrophilic addition of unsymmetrical alkenes to form a minor and a major product. All right, let's get into it. Let's go. The alkene 3-methyl pent-2-ene, we got the structural formula here, reacts with hydrogen bromide to form a 3-broma 3-methyl-pentane and 2-broma-methyl pentane, 2-broma 3-methyl pentane. The alkene 3-methyl pent-2-ene exists as E and Z stereoisomers. Draw the structure of Z3-methyl pent-2-ene. Okay, so when drawing these isomers, we want to first of all focus around the fact that they are EZ isomers, stereoisomers, and they're formed because there's no rotation around the double bond. The double bond is a planar area of the molecule, and there's no rotation around it. So that is my starting point for drawing a stereoisomer. Now it says pent-2-ene. So I know that this is the second carbon. I might make this one the second carbon. So I'm going to go ahead and add a carbon here. And this could be, I'm drawing a displayed formula here, but you could do this as a skeletal formula as it doesn't specify, got to be displayed, etc. So now how many more carbons do I need to make pent? So I know that that is carbon 1, that is carbon 2 because it's pent-2-ene. So I'm calling this carbon 1, carbon 2. I need 2 more carbons in the main carbon chain. So I'm going to come off, say, down here, and I'm going to go, and you're going to have to bear with me. I'm going to make adjustments later on. The whole point is that I'm going to show you the incorrect way first, and then I'm going to make adjustments before you start screaming and throwing things at the screen. All right. So now I have a pent chain, don't I? I have 5 carbons in a row, and I've got the double bond on carbon number 2 if that's carbon number 1. Now we're told there's a methyl group coming off. So 3-methyl pent-2-ene. So I can put a methyl group coming off of carbon 3, if that's carbon 1, 2, 3, 4, 5, then this is where I'm going to put my methyl group. And lastly but not least, I'm going to smash a hydrogen there. Now, this isn't necessarily right. I need to check. So what we need to check is that Z, what does Z mean? Z means zusammen, which means sisters. So when you have, it means you should have two of the same group on either side of the double bond. Okay, now in order to be a Z or E isomer, each of these carbons, so each of these carbons should have a different group attached. So you see I've got an ethyl group and a methyl group. That's fine. I've got a hydrogen and a methyl group. That's fine. But each carbon must have two different groups attached. You can't have an EZ isomer where you have a methyl group here and a methyl group there. That's impossible. You can't have an EZ isomer where you have a hydrogen coming off this carbon and a hydrogen coming off down below. Okay, they have to have two different groups attached. Now, because all four groups or the groups aren't identical and split into two easy pairs like chlorine atoms and hydrogen atoms, I've got to use the Chern or Kern-Ingold principles basically to work out what's high priority and low priority. Now, as it's sisters, I need to have both low priorities on one side and both high priorities on the other. Let's just check that. I'm going to start here and I'm going to call this, this is my first carbon. We could call this carbon A, right? Just for reference. And we could call this carbon B. So I'm looking at carbon A and I'm going to say, what have I got here? Hydrogen has an atomic number of 1, so that is going to be my lower priority. And down here, this is my methyl group with a atomic number. The carbon atom on the methyl group has an atomic number of 12, so this is going to be my high priority. So I've got a low priority on that side of the double bond and a high priority on this side. Now let's go to carbon B and let's check this one. Right here, this has an atomic number of 12. Oops, this also has an atomic number of 12. What do you do when the atomic numbers are equal on the first atom? You go to the next atom attached. And if I go to the next atom attached here, it's a hydrogen. And so the next atom attached has an atomic number of 1. So this is going to be my low priority once again on this side. And why is that? Because here, the next atom attached is another carbon with an atomic number of 12. So what I can say here, or a methyl group. So what I can say here is this is high priority. And that means that this is a Z isomers. I've got sisters, two low priorities on that side and two high priority sisters on that side. So the sisters, when you have E, entogen, it means opposite. If it was entogen, I would have my methyl group there and an ethyl group here. So I'd have like low and high across from each other. They'd be opposite each other. I'd have like one high priority there and one high priority there. But so this methyl group would have to be up there and this hydrogen down here, and then that would be an E isomer. But this is a Z isomer. Anyway, I've over talked about that. But here we go, folks. That is how to do that one. Now you can do the skeletal formula for that. I'll put that up here. Right, let's move on. Okay, we're down to 7.2. Name and outline the mechanism for the formation of 3-bromo-3-methylpentane from this reaction of 3-methylpentoene with hydrogen bromide. Explain why more 3-bromo-3-methylpentane is formed in this reaction than 2-bromo-3-methylpentane. And this is worth 7 marks, so let's get into it. What I'm going to do here, you could explain this all in words, but you could also get sort of 5 out of the 7 marks from the diagram alone, or you probably get all of the marks from the diagram alone if it's clear enough. So I'm going to go ahead and do the diagram. First of all, I need to draw the main reactants, which are 3-methylpentoene and hydrogen bromide, and that's going to get me the first marks on the board. So first things first, as this hydrogen bromide molecule approaches this electron-rich area, which is the double bond on an alkene, this is going to become slightly positive, and this is going to become slightly negative. I mean, that will have already happened because of the difference in electronegativity between the bromine atom and the hydrogen atom. And what we've got to do here, and this is going to get us our first mark, we want a curly arrow coming from the double bond because only electrons can move. Protons are stuck in a nucleus, they can never move. And we have to make that clear that that curly arrow is going to the positive hydrogen, like so. And as hydrogen only has one electron, if you imagine its box orbital, it has like 1s1, so it has one electron, right? When it is bonded like it is to bromide, then it also has an electron from bromide. There is no other way that hydrogen can accept any electrons like it is from this double bond without breaking this bond here. It has to make space to accept these two electrons. So in order to make space for these two electrons from this arrow, it has to get rid of the two electrons that it already has with the one shared from bromide. And it's going to do that by breaking this hydrogen bromide bond. Make sure you draw this curly arrow touching that bond, or as close to touching as you can get, and then coming down to the bromine. You don't want the examiner to think that you're doing that. That would not get you the mark because the examiner will think you're saying the electrons are coming from the hydrogen and not the bond. Okay, there we go. So let's make sure we do that. Right, that's the first couple of marks on the board. Right there. You're showing your electrophile, this hydrogen atom with a delta positive sign, and you're showing a curly arrow from the double bond to the hydrogen and a curly arrow from the bond to the bromine. Wonderful. Now we're going to show that we can form two possible intermediates. And here are the two intermediates, and these are really important for explaining why we get a major product and why we get a minor product. So I'm going to go ahead and redraw this out. Okay, so in this first intermediate, this is known as a carbocation, and this is a special type of carbocation. Carbocations are not the carbon atom with the positive charge. A carbocation is the entire molecule, but the positive carbon on the carbocation is where my bromine is going to attack. So my bromine that has snapped off from here now has a lone pair and a negative charge. And so we need to do that. And we need to show a curly arrow attacking here. Now, what is this going to form? Well, when we draw that bromine on here, this is going to be 1, 2, 3, 4, 5 pentane. And we're going to have, this is going to be 3 bromo, 3 methyl pentane. So this is going to be 3 bromo, 3 methyl pentane once this is joined together from this carbocation. And this is the major product, and there's a reason why this is the major product. So this carbocation is very stable as it is a tertiary carbocation. Now that's very important that you call it a tertiary carbocation. Of course, you can write a little 3 with a dot to stand for tertiary. So it's a tertiary carbocation. It has 3 alkyl groups, all electron kind of donating. They having an inductive effect, stabilizing the plus charge on the carbon atom. So this is making, that's a lot of waffle there, isn't it? So this essentially over here is making this molecule, this tertiary carbocation, is more stable because it has, and I'm going to show you here, it has an ethyl group here, that's an alkyl group, a methyl group here, and then another CH2, CH3, another ethyl group there. And all of these are, their electrons are being drawn towards this positive charge, and the electrons are cancelling out that positive charge, making this the more likely carbocation to form. And therefore, this explains why 3 bromo 3 So this explains why I've got to write that blooming thing out. That is so long. 3-bromo. Oh my good gosh. 3-methyl pentane um, is the major product. Okay. The key terms here. Yes, I need to show the bromine like that. Yes, I need to draw the correct carbocation like I have there. And I also need to say that this carbocation is a tertiary carbocation. Okay. And this explains why this is the major product. And I really need to compare it to the other one and say it's more stabilizing, which I could say here, but I want to draw the other one out first. And then I'm going to compare that and say that the minor product is less stabilizing. So I'm just going to go ahead and draw out the minor carbocation and therefore which leads to the minor product. Let's go. Okay, now in the alternative version, the hydrogen atom over here that first attaches to either carbon of the double bond, obviously our single bond has broken because it has formed the bond with the hydrogen. In this version, the hydrogen atom has formed here. So I'm going to circle that. That's this hydrogen atom here. It has attached here, leaving this as the carbocation. However, this carbocation is not as stable as this one. And I'm going to explain why, and I will circle in pink. It has a methyl group attached, but it's got a hydrogen atom, which doesn't have much of a sort of positive inductive effect. It doesn't really donate those electrons. This does, this R group here, this methyl group. And then we've got this group here is also over here, this group is also donating some electrons. So what I have over here are 2 R groups. You can call these R groups, alkyl groups in your answer, or and they are donating their electrons or allowing their electrons are having an inductive effect on the positive carbon atom in this carbocation. But because there's only 2 R groups compared to 3, we call this a secondary carbocation. So what I'm going to do is I'm going to say here the secondary carbocation formed is less stable than the tertiary carbocation, as it only has 2 alkyl groups with an inductive effect on the carbon. So this carbocation is, I think I already said this. Did I say it was less likely to form already? Is less likely to form. Hence, 2-bromo, 3-methyl. This is why organic chemistry kills some people. It's so long-winded. Pentane is the minor product. Okay, and that should get us all of the marks. What we're doing here is just justifying why this one is less likely to form. And we're going to put the lone pair there. We're going to put a little negative sign and a curly arrow from there to show it attacking the positive carbon on this carbocation. Remember, the carbon atom is not the carbocation. The whole thing is the carbocation. This is the positive carbon on the carbocation. But what we really want to get the gist is that the second carbocation, this carbocation, is less likely to form because it's less stable, because it only has 2 R groups, and each R group has a stabilizing effect on this positive carbon atom. But as it only has 2 R groups, there's less of an inductive or stabilizing effect on the positive carbon atom. And so the carbocation is less stable than this one, which has 3 R groups, which has a greater inductive effect on the positive carbocation, on the positive carbon atom. And so we're much more likely to get 3-bromo, 3-methylpentane as the major product, whereas here 2-bromo, 3-methylpentane is going to be the minor product. Okay, and that should get you all of the marks. So I'd expect you to get another mark for the correct secondary carbocation, and then marks for pointing out that it only has two alkyl groups and that the carbocation is less stable, therefore less likely to form. And that's going to get you all of the fat marks that you want for this 7 marker. All right, guys, I hope that helps. Don't forget, sharing's caring. Hit the like, punch up the bell, subscribe. Let's get to the marks, smash them exams. I'll catch you on the next vid.
You're still here? It's over.
Okay, when an aqueous solution of ethanoic acid reacts with magnesium, the progress of the reaction can be followed using the equipment shown in figure 5 to measure the volume of hydrogen produced. So we've got a gas syringe, we've got ethanoic acid, we've got a magnesium metal, we've got a bung, we've got a test tube. Figure 6 shows how the volume of hydrogen produced varies with time when 396 milligrams of magnesium are added to 30 centimeter cubed of 0.6 mole per decimeter ethanoic acid. You know what I like to say? I like to say highlight the stuff. So I'd be highlighting this and going, right, that's mass. Soon as I know that that is mass, you're probably at some point in this going to want to do mass over mR times moles. That's the crustiest little triangle you've ever seen. And then you've got volume there, haven't you, centimeter cubed, and you've also got concentration. And that generally means you're going to at some point need to do N over C times V. There we go. So this is an amount of substance question. As you can see, we've already identified the key points. Let's get down and check out figure 6 and see what the actual command of the question is. So here's figure 6. We've been given the volume of the hydrogen. We can see that's going up over time on the x-axis, and then it levels off at a certain point. Okay, 8.1, the equation for the reaction between ethanoic acid and magnesium is shown. We got 2 moles or 2 molecules of ethanoic acid, aqueous plus magnesium solid goes to magnesium ethanoate and hydrogen gas. With the AIDA calculations show that magnesium is in excess in this reaction. So what I want to do is focus on those bits. So we've got the magnesium, the mass, and we have the volume and the conc of the ethanoic acid. So why don't you pause the video, have a go, and then unpause and watch me go through the answers to this. Okay, here we go. So with the AIDA calculations, basically we need to do mass, 396 milligrams is the mass. Bearing in mind we need to convert that to grams, so it's actually divided by 1,000, you get 0.96 grams. We're going to divide that by the MR, and that's the magnesium. The MR or AR in this case, because it's not a molecule, is 24.3. And that is going to give me my moles of magnesium. Now, I'm going to write this down as 0.01629, and that is the moles of Mg. What I need to do now is work out the moles of ethanoic acid. So in order to do the ethanoic acid, we were given the volume. Now, I believe the volume was 30 centimeter cubed. We need to change it to dm. So we're going to divide by 1,000, and we're going to times our volume by our concentration, and the concentration was 0.6. All right, it was 0.0, but it's the same thing as saying 0.6, and that was mole dm minus 3, or mole per dm, you know, there we go. And that's going to give us my moles of ethanoic acid, and the moles of ethanoic acid are 0.018. So at first glance, my moles of ethanoic acid, remember, what's the formula for ethanoic acid? It's CH3COOH. So I've got my moles of ethanoic acid, and at first glance, you go, oh, 0.018. The magnesium, we've got less magnesium. That's the limiting reagent. But they've told us that magnesium is in excess. Well, how can it be in excess if we've got less moles? Well, what we need to do is come up to the equation and see that we need 2 moles of ethanoic acid for every mole of magnesium. So we can show that the magnesium's in excess and that we have left over, because what we can do is we can say, well, how much magnesium do we need to wipe out this 0.08? Well, as the ratio between Mg and ethanoic acid is 2:1, or 2 ethanoic acids to 1 magnesium, I can say, well, I've got 0.018 magnesium, so how much ethanoic acid, how much magnesium do I need? Well, divide it by 2. And that's exactly how much magnesium you're going to need. And I only need 0.009 moles of magnesium. And I've got way more than that. I've got 0.01629. Another way of us doing this to show that the magnesium's in excess, another calculation we could use to show it's in excess is we could say, well, how much ethanoic acid do we need? Well, if I've got 0.01629, I could times that by 2 and say, in order to use up all that magnesium, I would need 0.03258, but actually we've only got that. So that's how much ethanoic acid you would actually need in moles, and we don't have that. So again, there are different ways. 8.2, the reaction was repeated using 20 centimeters. So remember, they used 30 at 0.6. So we're going to 20, a smaller volume, but a higher conc. So how do we know that? Well, look, they used original was 30 centimeter cube. That's a higher volume. It's about 50% higher, isn't it? 30 centimeter compared to 20. And the original conc was 0.600, so like 25% less than the new conc. So we've got a lower conc and a higher volume. So what we want to do is we're going to look at, okay, so we've been asked to draw a new line for the new concentration. So the original ethanoic acid was 0.6 as the conc times the volume of 0.03, and that gave us 0.018 moles. And that told us roughly the moles are equivalent to what was the ratio of ethanoic acid to hydrogen? Let's check it out. Where's the damn equation? There it is. So it's a 2-to-1. So essentially, we're going to make 1, 2, 3, 4, 5, 6, 7, 8, 9, whatever. So we're making 0.09 moles of hydrogen, right? Because it's 2-to-1 with the hydrogen. You get the idea. Anywho, that's how much hydrogen gas is coming off there at this point. However, they've told us that they're changing the conc. What are they doing? They're increasing the concentration. But this time, they're doing 0.08 times 0.02, and we can work out the new moles of hydrogen, and that is going to be 0.016 moles. Now, as it's 2-to-1, the ethanoic, that's the moles of ethanoic acid, but it's 2-to-1 with the hydrogen. We're actually this time going to finish here. We can only make a maximum amount of 0.08 moles of hydrogen. So I know my line's going to finish there. However, the concentration is higher here than it is here. And that means there's more particles in the same space. So we've got more reactant collisions, got a faster rate of reaction. So I want a steeper line, but a line that then plateaus and ends here. I can't make any more than that because my limiting reactant is the hydrogen, and I have less moles of hydrogen than I did originally. So I want to be about 1 square down. Coolio. Hope that helps. Don't forget sharing's caring. Hit the like, punch up the bell, subscribe. Let's get to the marks.
You're still here? It's over.
All right, what I suggest is you pause the video, have a go at each of these. These are nice and easy. You can either do them in your head, A, B, C, D, or you write the answers down as we go, and then you check them off and see if you got them right. You'll want a bit of paper, and you'll definitely want a calculator and a pen. Let's go. Which of the following compounds would form an orange-red precipitate when heated with failing solution? Hopefully, you know that Tollens, silver nitrate, and the failing solution, which is basically very similar to Benedict's solution in biology. Hopefully you know which one of these functional groups they're good at identifying. So carboxylic acids, no. Nitriles, no. Ketones, no. We are looking, folks, at aldehydes, and there we got ethanal, so you should be able to spot that's an aldehyde. So our answer here, failing solution, we're going to get that brick red, blue to brick red, and we're going to get that when it is an aldehyde. Yeah, so great. So Hopefully you did well there. Let's move on. Question 10. Pentane nitrile can be made by the reaction of 1-bromobutane with potassium cyanide. Which of these is the correct name for the mechanism for this reaction? So what we've got to think of here, I'm going to very quickly draw it out. Not going to draw all the hydrogens because that's just too long. So here's my bromo, 1-bromobutane. And obviously that's delta positive, that's delta negative. We're looking at pentane nitrile. So we want, got that cyanide ion, you know, whatever, with the negative, arrow going there, that splits off there. What do you call that, guys? And of course, that's going to form a pent, because you extend the carbon chain with that. But what kind of reaction is this? Hopefully you've got it. It's nucleophilic substitution, because the bromide ion is lost and the nitrile my gosh, nitride ion is gained. Okay, can barely speak. Right, let's move on. Propane can be made by the dehydration of propan to ol. Right. Thank you for that. What is the percentage yield when 30 gram of propene MR42 is formed? So that's the product, the propene 30 gram MR42 are formed from 50 grams of propan to MR60. So what we need to do here, ladies and gents, we need to do mass over MR times moles. And we need to think about calculating the are formed from. So we need to know what our maximum mass is. It's going to be a 1-to-1 reaction, propene to propan 2-ol. So I want to work out, first of all, what is my theoretical maximum yield, which is going to be the moles of this. So I'm going to do 50 Gs over 60 as the MR. And what does that give me? I think that gives me something like along the lines of 0.83. I'm going to be a bit roughly, because there's quite a few percentages between points between that, so it doesn't matter too much. Right, that's my moles of propan 2-ol. So in theory, if I want 100% yield, I should be making 0.83 of propene. But what have I actually made? Let's check it out. I've got 30 Gs over 42. This is going to be like 70 or 80%, isn't it? What is that? 30 over 42 equals 0.71, roughly, folks. So we're just going to do 0.71 moles for my propene over the maximum theoretical yield of propene, which is equal to the moles of propan 2-ol that we started with. And we're going to times that by 100, and we are going to get roughly 86%. And of course, that is D. Nice. Oh, sorry about that. Little scream. Lost where I was. Question 12. Sulfur dioxide is produced when some fossil fuels are burned. Which of the following statements is true? So we're burning fossil fuels. We've got some sulfur dioxide coming out the top. Sulfur dioxide can be removed from waste gases in a power station by an acid-base reaction with calcium oxide. Ooh, they call that little chimney the flue. And yes, you can neutralize sulfur dioxide, because sulfur dioxide, any non-metal oxide tends to be acidic, whereas metal oxides are basic. You should know that, alkali metals, etc. Blah 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 blah. So sulfur dioxide is insoluble in water. No, it's not. It's soluble in water. It forms acid rain. Sulfur dioxide is a basic oxide. No, we just said metal oxides are basic, like sodium oxide, not non-metal oxides like carbon dioxide, nitrogen oxides, and sulfur dioxides. They're all acidic and form acid rain. Sulfur dioxide is ionic. No, it's covalent. They're both non-metals. So we know all of these ones are wrong. Yeah, that's right. Let's move on. Enough whiffle waffle. Okay, 13. I'm going to have to shrink this. Bosh, we got them all in. A, B, C, D. Which of the following is the correct mechanism for the formation of 2-mether-but-2-ene from 2-bromo-3-mether-butane? Right, folks. What happens here is, for the correct equation, the hydroxide ion must attack a hydrogen atom on a carbon that is adjacent to the carbon with the bromine on. So this is a viable reaction. See, the hydroxide ion is attacking that hydrogen. It's going to eliminate a water molecule. And the bond there is going to come here and form a double bond here. However, what's the name of this going to be? This is not going to be 2-methyl-but-2-ene. That is not going to be 2-ene. That's going to be but-1-ene. Okay, 3-methyl-but-1-ene. That is not the correct answer, even though that mechanism is completely correct. Okay, so let's move on to B. What we got going on here, again, the same as there, we've got the hydroxide ion donating its lone pair of electrons to this hydrogen. It's going to eliminate as water. The two electrons within this covalent bond are going to be slapped down there, and we're going to get 3-methyl, butene. So yeah, the formation of 2-methyl butene. Hold on a minute. Oh, what am I on about? Give it the lowest ranking, Tom, you wally. That's going to be 1, 2. That's going to be 2-methyl butene. That's our correct answer. I don't know why I said 3. I was counting from the wrong way. I was counting that way. Okay, so lowest possible answer is 2-methyl butene. That is definitely the correct answer. Now, the formation of the double bond must be either side of the carbon where the bromine atom is attached or the halogen is attached. So always check to the left and right. That's what you can make of the carbon with the halide attached. The hydroxide ion attacks a hydrogen on the adjacent carbon to the carbon with the halogen attached. Anyway, enough whiffle waffle. We're going to see why these ones are wrong. I'm going to go through these. So C, we've got the hydroxide ion. It's attacking a hydrogen, but it's attacking a hydrogen attached to the carbon with a bromine, so that doesn't happen. Okay. It would have been correct if it attached this hydrogen or this hydrogen here, which are adjacent to that carbon. Okay, this is also incorrect because it's attacking the carbon. The hydroxide ion is actually attacking the carbon, so that's incorrect, as well as it being the carbon with the bromide attached, which doesn't happen as well. So yeah, that's the correct answer. Enough of my whiffle waffle waffle. Let's move. One of my problems is over speaking. I've had it my whole life. It's called verbal diarrhea. Okay. 14, an organic compound is found to contain 40% carbon, 6.7% hydrogen, and 53.3% oxygen. Which of the following compounds could this be? Listen, guys, what does this remind you of? This reminds you of empirical formula, because they've given us the percentage of the different compounds, so we need to calculate the empirical formula and then work out which one of these would have the molecular formula in the same ratio as our empirical formula. So I'm going to do 40 over 12, and if I do 40 divided by 12, I get like 3.33 recurring. So that is for carbon. Let's check out hydrogen. Hydrogen's going to be 6.7 over hydrogen's mass, which is 1. So I'm going to get like 6.7-ish, which is like double that. And then that's supposed to be hydrogen, look like 11 there. And then for the oxygen, I got 53.3, and that is over 16. And that is going to equal 3.33. So we kind of got a ratio here. Right, we're going to divide all by the smallest. When you want to work out the ratio, divide everything by the smallest. So we go 1. So we kind of got, oh my God, I don't need that big fat. So fat thing there. Right, so we've got C. And then if I divide that by 3.33, I've got H2. And then if I divide that by 3.33, I've got another 1. So it's CH2O. And all you've got to do is draw out the molecular formulas to these, or the displayed formulas, and see, are they a ratio of that? So if we do ethanol, let me show you, right? If I do ethanol, oh my days. So if you bust out ethanol, look, I've got 6 hydrogens, 2 carbons. So that's a ratio of 3 to 1 of the carbon to hydrogen. So we're already wrong, because the hydrogen should just be double the carbon. And I've only got 1 oxygen in there. So like that's not the correct ratio. Whereas if we do ethanoic acido, let me rub this out, guys. All right, if I make some space and do ethanoic acid, with ethanoic acid, we're looking at oxygen there, OH there, and then we're looking at hydrogen, hydrogen, hydrogen. So I've got a formula that is C2, oh my days, H4O2. Check that out, 2, 4, 2, 1, 2, 1. That is the same ratio as our empirical formula. So that is our correct answer. That is the empirical formula for ethanoic acid. CH2O is the empirical formula for ethanoic acid. So I won't even bother checking the next ones. You know they're going to be wrong. So bish bash bosh. Let's move on. Oh my gosh, we've got the repeating unit of a polymer is like this. So that's the repeat unit, right? And what they're asking us is, which of the following molecules would form a polymer containing this repeat unit? They're basically saying, which one of these is the monomer that makes that? Now, the problem I have straight away, I'm going to locate these two, right? We've got E and Z. Problem with EZ is there's no rotation around the double bond. You can only get EZ isomers if each one of these carbons contains different groups. And this carbon here contains identical groups, and so does this. So it's impossible for this to be E or Z, or come from E or Z, because essentially what this has come from, let me show you what this has come from. This has come from this, right? So that's come from that molecule. So that cannot do EZ. So we can bash those two out. So it's either going to be butanene or methylpropene. Now let's have a look. This can't be bute, can it? Can't be bute because the longest straight chain without going back on myself is 3 carbons. So this has to be called, this molecule would be, let's say that is the main chain. So we got 1, 2, 3. This looks like methapropene. Yeah, there we go. You know, like 2-methaprop-1-ene, but you get the idea. It's methapropene. Nice. Okie dokie cocoa. Let's move on. Figure 7 shows a typical energy distribution for particles of an ideal gas in a sealed container at a fixed temp. Here's figure 7. We've got the number of particles, we've got the energy, we've got the activation energy, and then we've got A here. It says, which of the following statements is true? So position A represents the mean energy of a molecule in the container. No, the mean energy is normally to the right of this highest peak, so about there. The addition of a catalyst moves the position of the EA to the right. If I add a catalyst, no, it doesn't move the activation energy to the right. Because if the activation energy moved to the right, then we'd have less molecules that were actually reacting. So that would be no good. We'd want the addition of a catalyst to move the activation. EAC should be back there, meaning that less energy is required for a successful collision. Okay, so it's neither that nor that. The area under the curve to the right of EA, that's here, represents the number of molecules with enough energy to react. Yeah, that's true. You've got to be above the activation energy. You've got to be above the activation energy to have enough energy to have a successful collision. So that is a true statement. Let's look at why the last one's wrong. The position of the peak of the curve at a higher temperature is further away from both axes. I'm not going to get my head around what that says because I know that one's right. The peak of the curve at a higher temperature. Well, if we use a higher temperature, remember it shifts. So it shifts, whatever. Yeah, no, that's wrong. The peak of the curve is going to be closer to this axis. So that's definitely wrong. Anywho, let's move on. It's not going to be further away from both axes. Okay, tetradecane C14H30 is an alkane found in crude oil. When tetradecane is heated to a high temperature, 1 molecule of tetradecane decomposes to form 1 molecule of hexane and 3 more molecules. Which of the following could represent this reaction? So this is like a word trick game thing, right? So all of these show tetradecane, so they're all correct about that. But they've told us it decomposes to form 1 hexane, all of that doesn't make hexane. Let's get rid of C. That makes pentane. So we want to go through and just check this. Each one is heated to make 1 molecule of hexane plus 3 more molecules. So 1, that makes hexane and 3. That makes a molecule of hexane, but just 2 more molecules. So that one's wrong because it's got to be hexane and 3 more. So that makes hexane and 1, 2, 3. Okay, so these bad boys are all viable as into this sentence. Both of A and D make a molecule of hexane, C6H14, and they make 3 other molecules. 1 there, 2 there, 1 there, 2 there. Now we just need to check, do they balance? So 6 carbons, 10 carbons, 2 times 2 is 14. Yep, the carbons are balanced. Boom! 14 hydrogens plus 8. What's that? 22 plus 8, 30. Boom! A is balanced. So A is going to be the correct answer. Let's spot why D is incorrect, guys. So we've got 6 carbons. We've got 8 carbons. 2 times 3 is 6 plus 8 is 14. The carbons are balanced. Ooh, 14 hydrogen plus 6 hydrogens, 20 hydrogen plus 2 times 6 is 12 is 32. Oh, we got 32 hydrogens on this side. That can't be right. There we go. Let's move on. Yep, I'm drinking coffee today. Excuse me while I have a slurp. Okay, the structure of cyclohexene is shown. Which of the following is the general formula of cyclic alkenes such as cyclohexene? So first of all, you know the formula for alkanes is CnH2n plus 2, right? So like hexane would be C6. I don't even know what I'm doing here. C6H14. That would be hexane. Now, what about for cyclohexane? Well, cyclohexane has 2 less hydrogens, so it's just CnH2n. So cyclohexane is CnH2n. I think I've just gone off on a bit of a waffle here. And that's because you can only have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So you because you connect the ends of the molecule when you make it cyclic, you lose 2 hydrogens. Not only have they collected the ends of the molecule here, but they've also added a double bond, so we're losing another 2. So it's CnH2n minus 2. I don't know what I was just getting into there. There's going to be a big, long explanation for no reason. You can just memorize that, really. Okay. Gosh, 3.5 weeks, still getting over a chest infection. A and B react together in this reversible reaction. Okay. A mixture of 10 mole of A and 10 mole of B were left to reach equilibrium. The equilibrium mixture contained 4 mole of B. Okay, what is the total amount in moles of substances in the equilibrium mixture? I'm going to do the ICE, right? You know the ICE, don't you? So initial, change, equilibrium. Can make a little table like this. And this is the number of moles of each. So I'm going to be like A initially, and then B initially, and then C initially, and then D initially. Right. So what is the total amount of moles of substances in the equilibrium mixture? Oh my gosh, I'm throwing stuff all over the place. Oh, what have I done here? Oh man, I don't even know what I'm doing. Here we go. Oh, oh my good gosh. Right. Okay, sorry about that. I was like choking on coffee there, having a serious choke out. Right. What have we got? We got initially you have no reactants. So you're going to have 0 of C, 0 of D. Initially, it tells us we had 10 mole of A and 10 mole of B. Lovely bubbly. Thank you. Now, it does then tell us that the equilibrium mixture contained 4 moles of B. And this is your starting point. So you now know that B changed by 6. Therefore, peeps, we now look at the ratio and we go, what is the ratio of B to A? So we're going to deal with A first. So the ratio of B to A is 3 to 1. So the change is 3 to 1. So 6 divided by 3 is 2. So A changed by 2 moles. How many were left over? 8 moles. Brilliant. Now we're going to apply the same technique here. We're going to go from B, or we could do A. A might be easier to do. So A changed by 2, which tells me that C changed by 2. Or if you like to do B, you can say, well, B to C is 3 to 1. So we're going to have the same thing, 3 to 1, 6 divided by 3. C changed by 2 moles. And as there was 0 at the start, it means there were 2 moles at the end. And then we're going to do the ratio. Now, you might find this a little bit harder. If you go from B to there, you've got to go, but you've got to times it by like 2 over 3 or whatever, blah, 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 is 3 to 2. It's easier just to go from A, right? A changed by 2, and D is in a ratio of 1 to 2, or you can say, you can go from C. C's in a ratio of 1 to 2. So it means that D changed by 4 because it's 1 to 2. So you times that by 2, and that means that at equilibria, we have 4. Now we just got to add up the total amount of moles in the equilibrium mixture. So we've got 8 of A, 4 of B, that's 12, 2 of C, that's 14, 4 of D, that's 18. The answer is C. There you go, folks. Okay, don't forget to like the video, please. Enough time people watch my video and they can't be bothered to hit the like. It massively helps me out. Do me a favor. All right. Let's move on. Right, we are up to question 20. The MR of hydrated copper sulfate CuSO4.5H2O is 249.6. Which of the following is the mass of hydrated copper sulfate required to make 50 centimeters of 0.4 mole per decimeter solution? So what I'm going to do straight up the bat is I'm going to say, what have we been given? Well, I've been given volume, peeps. That's not volume. What the arse? That is concentration. Over here, this is the volume. Of course, you've got to change them into the same units. As soon as you've been given volume and conc, you know the coup, N over C times V. Let's get to it. So I want to go 50 divided by 1,000. Why? Because you have to change that into decimeters because the units are different. And then times 0.4 is really me doing V times C, and that's going to give me moles. So what does that equal? If I do that times that, it's going to give me 0.02 moles, right? So that's how many moles we've got. Which of the following is the mass required to make? So now I just need to times that by the MR to find how much mass I would need to divide in that. Like, so we've got 0.2 moles in 50 centimeters, right? What's the mass that I need? Well, times that by the MR and you're going to get mass. How did I know I got to do that? Well, it gave you the MR, peeps. So if they're giving you the MR, that means you're going to have to use mass over MR times moles. And we just calculated the moles. So let's do 0.02 times 249.6. What does that equal? That equals 4 0.992 something or other grams. So my answer is D. Boom. Okay, moving on. Equilibria, my favorite. Questions 21 and 22 refer to the production of hydrogen. I've been watching Despicable Me with my daughters. Sorry about that. Question 21 and 22 refer to the production of hydrogen by the reaction of methane with steam. The reaction mixture reaches a state of dynamic equilibrium. We got methane, gaseous, steam. We got the reversible symbol. We got carbon monoxide plus 3 hydrogen molecules. And we got the plus 206. What is this telling me? That's telling me you're endothermic, buddy. I don't know if I need that yet. Let's read the question. Which of the following shows how the equilibrium yield of hydrogen and the value of the equilibrium constant are affected by the changes shown? 1 mark. Okay, if we increase the pressure, does the yield decrease? Let's check that out. So remember, increasing the pressure, I've got 2 gas molecules here. I got 4 gas molecules there. So if we increase the pressure, it's going to shift to the side with the least gas molecules. Yeah, that's right. That's a true statement, baby. That's true. But I don't know if this is true. The effect on the value of Kc. Pressure and concentration. You got to remember this. Pressure, under pressure, and concentration do not affect Kc. So pressure and concentration, changing the pressure and concentration do not affect Kc. So that's wrong. Add a catalyst, it will increase the yield of hydrogen. No, it doesn't shift the equilibrium position, so it can't do that. Okay, so I know that's wrong straight off. Catalysts increase how fast you reach equilibrium because they increase the rate of both the forward and the backward reaction by the same amount. So they increase the speed at which you'll reach equilibrium, but they definitely don't increase the yield. And that's true. That's a true statement here. They have no effect, but this is false. Okay, so that's wrong because we need both statements to be true. Right, what about if we increase the temperature? Will it increase the yield? It's endothermic, so if we increase the temperature to an endothermic reaction, basically you make it hotter. It wants to do the opposite because Le Chatelier said that reactions just, they're like that. They're contrary. They want to do the opposite, whatever you do. So it's going to shift to the right. It's going to shift to the endothermic side. That is a true statement. It will increase the yield. Increasing the temp of an endothermic will increase the yield. What's the effect on Kc? Well, if we increase the products, Kc is equal to products over reactants. So if we're increasing the yield, we're increasing P. That means we're going to get, when we divide it by R, we're going to get a bigger Kc. So this is absolutement true. Removing CO as it is formed will increase the yield. Hold on, removing carbon dioxide gas as formed. Well, I'm going with C. Anywho. Yeah, so as I was saying, this one's a little bit more tricky because you're like, yeah, if I remove the carbon monoxide, right, then it's going to cause these guys to shift to the right to make more carbon monoxide. So we are going to increase the yield. And then we say to ourselves, surely by my explanation, that increases the products over the reactants, right? Surely that increases Kc. Well, not really, because what you're really doing is decreasing the concentration of carbon monoxide. So you're changing the concentration. And when you change the concentration or the pressure, what do we say here? It has no effect on Kc. You might say, but doesn't P increase? It does. But the problem is that the P over R is a ratio and the ratio stays the same because the reactions are going in both directions, blah, 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 blah. So changing the concentration or pressure does not affect Kc. You just got to remember that. Difficult concept to understand sometimes. Right, let's zing. Well, it is for me anyway. Okay, 22. Some enthalpy data is given in table 3. Bish, bash, bush to be calculated. Use the information in table 3 and the stated enthalpy change to calculate the missing bond enthalpy. I mean, that's like back in the old GCSE days. This was like a fat 4 bloody marker. Anyway, yeah, this you've got to do this in 60 seconds to stay on time. So what did we have? We had CH4 plus H2O goes to carbon monoxide. Jeez Louise, that has not gone as planned. Okay, wowzer. So what I want to do is reactants minus the products equals 206. Let's work out these over here. We've got 4 of these, so I want to go 4 times 413, and that gives me 1652. I've then got H2O, so that's 2 OH bonds. So 2 times 463, what is that? That is 926. Let's add them together because them are reactants. And if we add them together, we get 2 0.578. I'm then going to put the minus sign because I always do reactants minus products equals the enthalpy change. Now we want to calculate the products. We don't have this yet. So I'm going to calculate this first. We've got 3 of them. So 3 times 436, I believe, is 1308. And then I want to put plus CO, which is the CO triple bond, equals 206. And so what we want to do is simplify this bad boy. And if we do that, we're going to do 2578 minus 1308, and that is going to give me 1270 plus CO equals 206. I now want to get it, so I've only got CO on one side, so I'm going to minus 1270 from both sides. Okay, see how this works out. So we're going to end up with 206 minus 1270 equals CO is equal to minus 1064. Not sure what I did there because I got a minus number and bond enthalpies aren't minus, but you can clearly see what the correct answer is. It's B. Don't know why I ended up with a minus. Probably some of the way I worked it out. Anyhow, bond enthalpies aren't exothermic. They're endothermic generally. Well, we generally don't assign to them. They'd be exothermic if they were being made, and if they were breaking, they would be endothermic. So we don't need the sign. Anywho. Let's move on, Tom, before you get yourself all in a tangle. 23. 2 moles of gas X are stored in a flask of fixed volume. Which of the following changes would lead to the greatest increase in pressure inside the flask? So which of the following would lead to the greatest changes inside the pressure? Increasing the temperature. So essentially what I'm thinking about here, right? Peeps. I mean, I don't know why I'm doing this. Why am I doing this? I must be some kind of moron. PV equals nRT. Fixed volume. Which of the following changes would lead to the greatest increase in pressure in the flask? So they're increasing the temperature there. So that's going to increase the amount of kinetic energy of the particles. That's going to definitely, it's going up by 180 degrees. That's definitely going to increase the pressure. Adding 1 mole of the gas into the flask at a fixed temperature. So they haven't increased the speed of the particle collisions, but they've increased the number of particles by 50%. 50% increase in particles, whereas here they've increased the temperature 10 times. So I think that is going to be a bigger factor on temperature than that. So I'm definitely going to get rid of B. What about if we add more particles, add 0.5 moles of argon gas, and we increase the temperature? Yeah, so they've got like a 25% increase in the number of particles. And our temperature has gone up like 7.5 times. So there we increased the temperature 10 times, but no particles. Here we did a 25% increase in particles and a 7.5 or 750%, whatever, increase. I don't know what increase that is, but yeah, it's a big increase in temperature. Not as big as that, but they've also done a 25% increase in particles. So I think that is less than that. And then this one, they've reduced the number of particles by 25%. So that would tell me we're having 25% less collisions, but then they've increased the temperature quite a damn bit as well. I'm going to go for this one. This is the one where both the temperature and the number of particles have increased. So I'm going for that one as going to have the biggest increase in pressure because we've got more particles in the same space, so more collisions, exerting a force over the area of the container. And we've also got the particles are moving at a higher speed because they've increased the temperature as well. So I'm going for C. There we go, peeps. Okie dokie. I'm sure we could have worked that out with doing PV equals nRT, but that's long and I ran out of so much time with my previous question. All right, guys, don't forget, Shavings Kevin, hit the like, punch up the bell, subscribe. Let's get to the marks. Hit the like. I'll catch you in the next one.
You're still here? It's over.